afternoon. I hope we are not going to make you sleeping after this heavy food. Thank you for coming. As you see, my presentation is challenging of material and corrosion management, stress corrosion cracking, and gapping in our understanding. Gapping is a big word, but you will see. I'm focusing on line pipe problems. Line pipelines has a lot of problems because they transport gas as well oil. And when the failure happen, unfortunately, it's very, very dangerous because many people die, and there's also pollution and all the consequences from economical point of view. As you know, the pipeline can experience stress corrosion cracking, corrosion fatigue, microbiological-induced, hydrogen-induced cracking, or hydrogen embrittlement. And also there is two mechanisms, high pH, which is intergranular mechanism, and near neutral pH, which is transgranular. This transgranular is a new finding. It was discovered in Canada in 1986. And everybody start to scream, yeah, we saw transgranular. Nobody said before we saw transgranular until somebody has to say we find something and everybody follow up. Now, why I say this is because for student, sometimes you listen to your boss and so, but you have to use your imagination, you go beyond what the people talk about it. Then I'll show you what's going on in this business. As you know, stress corrosion cracking or pipeline, thousands of kilometers, and there is soil, topography, and also water, cathodic protection, coating, and so on. Also the stress can be stress, hoop stress, axial stress, residual stress, cyclic stress. All this happen in pipeline. And also, I didn't talk about earthquake, and also if you are in the north, because I live in Canada, and when it's frozen and when defrozen, the movement of soil, and so all this create a movement on the pipeline, and imagine how this pipeline suffer. But they still say stress corrosion cracking. Now here is one experience. For example, you see the size of the car, of the trucks, and this is almost 100 meters. Unfortunately, 7 people passed away here in this incident. And mostly stress corrosion cracking, who are familiar with stress corrosion cracking, they can find thousands and thousands of cracks located in one area. And then you run kilometers and then find another colonies of cracks and cracks, thousands. But sometimes those cracks are, in general, are not dangerous. They are small, and they are closed by oxide film, because they start because of residual stress on the surface. The cracks start to open a little bit, and the corrosion take place, and those oxidation and corrosion can block, can be as a shield of the environment get in. I focus on this point. They said stress corrosion cracking. What is means a definition of stress corrosion cracking? It's the environment, stress, and the material susceptible. But the stress in pipeline industry, they believe it's constant. The parameters of fluctuation, they didn't consider it. I will show you where I find there is a gap in the way they explain a stress corrosion cracking. Now here, just to say, these small cracks are usually dormant and inoffensive. The critical step in near neutral pH failures in process by which these cracks are able to grow beyond critical depth. This mechanism is far being understood. This is a lot of things the student or professors in the lab, they can focus on to explain real mechanism. And we'll get at the end what kind of mechanism we believe is, but still a debate between researchers. To address the remaining knowledge gap on the effect of pressure fluctuation, crack growth in pipeline stimulated, a summary, I will give you a summary what is, I'm not saying conclusions, is Summary. Conclusions, it means you are sure. Summary, we observe. SCC in near interpretation is still contradictory. The results reported in full-scale test and a small-scale coupons static loading. We use static loading using parameters which industry give us. They spend millions of dollars. I worked 7 years on initiation, 7 years, using exactly what pipeline industry asked us to do. And believe me, we couldn't find any cracks, or we find cracks, but just the minor. And that's where I can say there is a gap in the way the industry understood the problem, and as researchers, the way you can go beyond and come up with real mechanism. Now, some researchers report that the finding of CC under static loading proven that cracking in near neutral beige conditions is authentic, means it's really under constant load. But in opposition, we suggest that stress corrosion cracking required dynamic loading. And I will show you, if you don't have dynamic loading in a pipeline in general, you generate pits, you generate small cracks, and it's closed, but you need dynamic loading to go beyond this initiation and makes failure happen. In addition, that long constant stress holding times close pits, cracks, and cut off the solution path. Therefore, magnitude of the increase in applied surface stress is important in crack initiation growth. In practice, pressure in gas transmission line is relatively stable over the time, but in liquid, there is a movement. Consequently, relative contribution of crack growth leading to and from static loading will be different in gas and liquid line. A generic approach taking into account all possible growth mechanisms is therefore needed. Generally, the main part of pipeline is consumed is crack initiation. And we find by using constant load, using 4-point bending, large surface, because when you have 4-point bending, you have large surface, you can have statistical analysis what's going on the surface, because you have homogeneous surface under same stress. The laboratory investigation, it has been found that earliest crack appears to initiate at corrosion pits that formed around non-metallic conclusions, and later crack growth from corrosion pits. That's how it's happened. This is in the field. What you find when you have cracks, you find thousands of cracks, and then there is a small cracks propagate, and this distance, it's critical distance small. You have plastic deformation overlap. It creates coalescence, and that's it came large cracks. Over the period of years, this individual crack might lengthen and deepen, and cracking within colony might be linked together to form a large crack. Evidence correlated the pits with non-metallic conclusion was obtained from a replica of the specimen surface before test. Now, if you want to really chase what's happened on the surface, because I said initiation is very important, but most of the people, they clean or they polish by using water. When you use water, you dissolve many inclusions or many elements on the surface. How we chase them? We use oil. We polish at certain level and we finish with oil. We don't dissolve what is on the surface. And then we make a replica. Then we have fingerprint of the surface before we start test. And every few hours or 1,000 or 100 hours, we take another replica and we find very important results. This is how it happened. Here, we find 5 inclusions. If you use water, you cannot see them. They will dissolve. But using water, which is neutral, we don't dissolve them. We find them. And then we say, okay, let us see under 4-point bending what's happened. 13 days after, you see the small cracks start to nucleate, and then 19 days start to grow up, 31 month, it start to link, and then after 1 month and a half, it links together, and then the failure happen. The inclusions are very important. But now you can say how these cracks grow if you have constant load. We don't have any progression. It's pit start and it grow by corrosion, and sometimes they dissolve when it grow up, and then it dissolve because of the environment. They take off the initiation and you have a smooth surface. We need to use certain level of the stress, and this is how it happened. When we load the sample under constant load, we don't have any initiation. And then when you start to load it, that cracks start to grow in perpendicular to the stress. Now, no clear evidence of a SCC mechanism. Although we have attempted to accurately replicate field conditions, it is believed that we might have underestimated the effect of stress razor, which appears to be important. When you talk to clients who give us millions of dollars to do experiment, and we said, we don't believe in constant stress. They are upset, this is impossible. And we demonstrate them what we find in the lab by using certain stress. We find the same morphology as shown in the field. Then they start to scratch their head, and I'll show you how we convince them to believe us, and then you can see now everybody start to say yes, 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 yes. There is not only stress cone cracking, there is component of fatigue take place, and we'll demonstrate it. Example, where the fair understanding type of corrosion, type of causes the stress cone prediction of location of SCC and operational pipeline is not well developed. Observation, there are a number of ways to grow small crack-like defect in pipeline steel in the laboratory, but we have failed to initiate full-blown SCC colonies as shown in the field. The failure to obtain crack initiation in the laboratory contrasts with predominance of short cracks on various pipelines in the field. Although we have attempted to accurately replicate a field condition, it is believed that we might have underestimated the effect of stress razor, which appears to be important for predominantly mechanically based initiation mechanism. Now, what should be done to convince the constant stress and all this verbiage of stress cone cracking is not 100% sure it's stress cone cracking? There is another component. And we use the field containing. What we did, we went back to the symmetry of the pipeline. We have many thousands. And we randomly, we chose pipeline, which already many companies, I don't want to name them, they get millions of dollars analyzing the pipe after rupture, and they said SCC. Let us see if it's SCC or not. Now, this is, we select from 24 pipes, we select 6 randomly, and then we find there is small cracks and the pits and so, We took this piece of pipeline, and it's there. This is the pipe, this one. And we did them all. And this one show you, because of time is short, we open it. We open this crack, this one. And we open this. You know how we do it? You take sample, you clean it, and then at the tip of your pits, you can put the notch behind, not at the front, behind. And then you dip it in nitrogen, and then with the hammer, you crack it. You open it. When you open with in the nitrogen, you see clearly where the crack happened and the nitrogen and the cracks in the field. Okay, now hats, and you see here, it's a zone 1. I don't know this. I think it's a dead. No. Okay, now here, this is the surface, and you see when you go down, 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 what we find Okay, that is very important. When you open your old surface, what you find a heavy oxide film. And you have to be careful how to clean it. We have techniques which you can clean a surface without damaging a wall of the surface. Because if you don't take attention, you dissolve it and you don't see it. That's what happened in most of the companies when they do analysis on fractured surface. There is techniques and where you should look at, and you find a fresh surface even years after. And you can look at it in the microscope and you see the evidence of really the mechanism. If you look at the beginning of the crack, it's already dissolved with time. Oxide took it out, eat it out. You have to look at the crack tip, few microns down, because it's still a ligament. You open it carefully, you clean it with specific chemical, and then you look at it in the microscope. What we find? We find the stress. We find the striations. You know, this is striations. Yes, it's too short. Okay. Now you can say, well, how you can say this is really realistic versus the field? Okay, this is the field, and this is the lab. We did in the full scale in the lab, and we mimic exactly the environment and mechanical testing. This is all pipe with the environment, and then what's happened? We open it, and we find striation. Those striation versus striation in the field, we make calculation, and we find stress intensity factor similar. This is the stress, and then fatigue crack growth rate in the field versus in the lab, we find almost similar stress intensity factor based in distance using Paris law and so. The implication of the results, just this is, this is very important. What we did the air ratio 0.5, 0.7, 0.75, 0.8, 0.9. And then we applied 0.7, we see crack propagate. When we go to 0.95, crack stop. That means when you have constant load, it's almost constant load, your crack stop. That means this is doesn't reflect what is happening in the field. Why cracks happen in the field? That means you have certain amplitude of. And then here, summary, the initiation of nerve has been underestimated as the conditions, and then the condition to ensure that the result of the study can be operated in pipeline. This is from viewpoint to point. This is the conclusions. We advise the company to control and stabilize the pressure of pipeline. And they start to do it. They saw the number or percentage of the cracks reduce tremendously by controlling fluctuation of their pipeline. That means we demonstrate is not SCC alone, but SCC plus fatigue. That's what I want to say. Thank you. Obrigado.
For the nice